All right, so the reasons why the Earth was assumed to be at the center of the universe, this actually goes back to Aristotle. And you got to remember Aristotle's also done a lot of incredible work in mathematics and geometry and things like that, but he is pushing this idea of an Earth-centered universe. So we don't have crystal clear vision of the time of the Greeks. It's a mixed bag. A lot of progress in mathematics, not so much progress in understanding the universe yet. So why do we think the Earth must be at the center? Well, reason one, the big reason. I mentioned this on David Letterman's Top 10 list. Probably get Donald Trump in there somewhere. Like Donald Trump. I'm not sure how that really works. But anyway, well actually, yeah, because Trump has to be the center of the universe. On the Earth has to be. So that would actually be reason zero. So reason one, the Earth doesn't feel like it's moving. Now, if we were flying around the sun, it would be at very high speed. I mean, they knew that because, oh, you bring up a baseball gun, you know that. But we don't feel like we're moving. We don't all get motion sickness at the same time. There's only a few people here and there, right? But if we were moving around at thousands of kilometers per hour, there'd be forces and we would feel, you know, then they had roller coasters back in before, so they knew about it. Motion sickness. Reason two, there'd be a strong wind. You know, why doesn't everybody have this kind of motorcycle hair? No. It was, you know, parties were all fine, and there wasn't any strong wind felt. Now, of course, that gets into the concept of that vacuum versus not having vacuum. They didn't know that there could even be such a thing as a vacuum. Thinking would be if Earth is moving through space, it's moving through something, you know, liquid, gas, something, and then if we're moving through that, we feel a wind, right? Concept of a vacuum. But the first two are pretty easy to argue around, but the third one is actually very interesting. We don't see something called stellar parallax. Now, if the Earth were moving around the sun through a background of stars that are at varying distances from us, then as we move along, like let me give you an example. Let's say this is a nearby star, and that thermostat is this. So if I'm the Earth and I'm moving around in orbit here, I'm seeing that nearby post thing, seeing it shift with respect to the thermostat. Right? A little bit of a shift would be seen because not all the stars are at exactly the same distance. So the nearby one would appear to shift back and forth with respect to the distant one. Just a perspective effect, almost like the retrograde phenomenon again. But that was completely undetected. So the thinking was the Earth can be going around the sun because we would see the perspective shift of nearby stars relative to distant stars. We don't see that. Well, that's actually a pretty good argument. And the answer to that argument turns out to be that there is, in fact, this stellar parallax. The shift really does happen, but it's so small you can't see it without a telescope because the distances are so vast. You know, the nearest star is 3 light years away. You're comparing that to a star that's a little bit farther away than that, but the Earth's orbital radius is only like 1,000th of a light year. So that, you know, the geometry is bases are so huge that even the nearby stars are super far away, so they don't seem to shift very much. Oh, so anyway, this actually is just a model where we actually have the Earth at the center. It's sort of interesting. We have the Earth at the center, then we have these spheres upon which all the other constituents of our system would ride, these crystalline spheres. We have the Earth at the center, then we have the lunar sphere. So it was acknowledged that the moon, of course, the moon does go around the Earth. They were dead on about that. That's no problem. And that sphere is the closest of all these other spheres. Logical, because the moon can move in front of anything else in the sky, right? You can actually see the moon move in front of Venus or Mars or times. So the moon's shell would have to be the nearest one. Then we work our way out to Mercury and Venus and the Sun, the solar sphere there. Mercury and Venus spheres had to be closer to the Earth because you could actually see that Mercury and Venus moved across the face of the Sun. Their crystalline spheres have to be closer than the sun. Then you get to the distant planets. So this is called the Ptolemaic model. It's basically the idea of Aristotle. But moving into the AD time period, going forward in time, we have more and more observations of planetary motions. Now, the priests, a lot of the priests were actually astronomers who were making note of planetary locations in the sky because this is part of God's creation, the universe. So they were interested to keep track of things like that. So there's a big crossover between religious scribes and astronomers at that time. And body of data about Mars. Mars is working. Years and years, Mars' actual position on the sky. Well, in order to get it to work, in order to actually have Mars be at the correct location, every time you make an observation, you can't use just a circle. You can't just have Mars riding on this sphere, the zone we were talking about a moment ago. You have to make changes. You have to add little additional elements called epicycles. So an epicycle is kind of a wheel stuck on top of a wheel. It's almost like it's kind of a gear riding on another gear, if you will. So what we do is, we have Earth here, and we have what's called a deferent, which is actually the crystalline sphere. Clear crystalline sphere. You can't see it. Mars is riding on that, but Mars isn't directly riding on it. The epicycle is riding on the deferent, and then Mars is executing a little loop on that epicycle. And you have to do that in order to get Mars to be in the correct place in the sky when you make your observation. You also, by the way, have to have a little bit of a shift for Earth relative to the center. They were actually still willing to live with that, because Earth is still right to the center. Okay, so we have to add these things called epicycles. And the epicycles have little periods of spin of their own. The deferents have periods of spin. And you have all this getting animated starts to give you this kind of a pattern of motion. As views from Earth, we are seeing both prograde and retrograde motion here. Going from 1 to 2, that's eastward motion, and going from 4 to 5 is retrograde motion, and followed by prograde motion. So you set up the spirograph kind of thing correctly. Anybody even remember spirograph? This is pre-internet phenomenon. So gears, you put pencils in gears, you make little loops, things like that, and you get patterns like this. Okay. So Ptolemy's model, so Ptolemy is a scribe who is the latest scribe taking care of this model. But the observations are accumulating, and you have to tweak things constantly to keep the agreement precise. Right, so this is just another figure from the book that shows the deferent and the epicycle. Narrative what we're talking about. If we show all the other planets, we start seeing, fairly complex motions. All of the outer planets actually execute this retrograde motion, so you have to have deference and epicycles for all of them. And of course, Earth is at the center, and we have the Moon, Mercury, and the Sun. Okay, so we have Aristotle with his Earth-centered universe in 350 BC. But even going back to that time, we have scholars who lived around the time of Aristotle and Archimedes who actually thought maybe the Sun is at the center. Maybe that actually is a more simple explanation for what's going on here. And it is a lot simpler, because if you put the Sun at the center, you get rid of the need for epicycles, which are kind of nasty things. You've got to mar your model by sticking these things in all over the place. So as early as 250 BC, we have Aristarchus arguing that the Sun could actually be at the center. But the geocentric model goes on for hundreds and hundreds of years, 250 to 140, and even beyond that. Okay, so this is just a shot of the Aristarchian idea, where it does have the Sun at the center. All right, so if we look at, right, so again, this is I think I showed you the Copernican model before, which is what's really going on. This is what ain't really going on, right? This is the Earth at the center, and you have these retrograde loops taking place. They come right there from Mars. And retrograde motion, that's retrograde motion. So this is the Copernican, this is the Ptolemaic view. Right, Earth at the center, you can get the retrograde motion, you can set up your deferents and your epicycles this way. There's the Sun. It's completely ridiculous, the Sun is going around the Earth there. Ptolemy takes the idea of Aristotle and keeps adding epicycles to get it to maintain agreement. Because remember, we're accumulating observations of Mars that are better and better quality observations. Okay, so we do have a logical structure here, which is the reason it lasted as long as it did. This model was around for thousands of years up until around the middle of the 17th century. All right, so it's a satisfactory description of motions of the Sun, Moon, and planet. It even could predict eclipses. Okay? I mean, there's that much going on there. If you set this thing up right, it's like a clockwork representation of our solar system. That doesn't really represent our solar system, but you can set it up so that it sort of in a kind of a logical way, at least, reproduces the motion, including eclipse. It does have predictive power. It's a coherent model with consistent principles. There's no little green men running around doing things. It's all based on spheres that are spinning and epicycles that are spinning. So in that sense, it's kind of sort of scientific because you don't have a deity actually reaching in and saying, oh no, wait, that's not going to work, so we have to move more over here, arbitrarily at this point in time. Something like that happens just under the clockwork universe. And it was in accord with the established scientific and even religious doctrines at the time. And it lasted, well, I guess you have to really argue it's the longest lasting theory in history, really. I mean, it lasted thousands of years. None of the modern theories have done that because they had modern science for years. So Ptolemy's model had to be continuously updated because of the fact that we had this proliferation, a catalog of observations of Mars growing over decades, telling us exactly where Mars is. Well, the model has to nail all those observations of Mars. It gets harder and harder to do that. You have to add epicycles, you have to take epicycles away, you have to prune, you have to change the periods of epicycles, or maybe the radius of an epicycle, and without a calculator too, by the way, all by hand. So as to keep the model in agreement with the observations. So I mean, the observations are the observations of God's universe. So you can't play with the observations as a given fact, right? You've got to make the model fit the facts, but you can't fudge the data or anything like that. So we have ultimately 80 circles, nested epicycles. So there was an epicycle riding on an epicycle. So even more complex motions end up being required to keep everything in perfect agreement with the observations of